So kind of a review of interfaces. We haven't looked at interfaces in a little while. Okay. So remember last time I told you I would talk about making your object serializable, and in this way your tree can remember things from when you start main and stop main. So you're going to write him to a text file. So this is in essence writing an object to a text file, which is done in a lot of programming languages. It's a way to save the state of a game. You're saving the state of your object, so you're saving your object as it appears in the game at that moment. And then when you start the game again, you get to read him and then start him where he left off. So you're using the same object again. Okay. Now remember interfaces. What are our rules for implementing an interface? You guys remember? What is the rule for implementing an interface? They're actually a pretty simple rule, or a couple rules. Remember, interfaces are kind of like a skeletal structure that we're saying we're going to be a serializable object. What was our rules? Somebody has to know our rule. It was only a couple of things. What do we have to do to make something? Remember, we were doing comparable interface. When we wanted to make something comparable, what did we have to do? Yeah, we just had to implement it. So all you had to do is put at the top of your code, implements, and then the interface name. And then what was the second rule? Which is implementing it. You just had to write all of the methods of the interface. Notice that this interface has no methods. All right, and you can read about this interface. I guess the link I had on the directions didn't work, but remember that you can just type in serializable Java and this API will come up. And you can read about him. Okay, I'm not going to read him in front of you. And remember that when you're reading this documentation, some of it might sound a little cryptic at first, but the more you read this documentation, the more it makes sense to you. So I just tell people, read it anyway. You'll get some of it, maybe you'll miss some. Look up some words as you go along. You'll get better and better at reading this stuff. And if your major is computer science, that's what you're going to be doing. You're going to be reading this stuff so you can make some new code, okay? So, you know, it does get easier. It does definitely gets easier the more you read it, okay? So you just have to make yourself read it at first, right? So read these APIs. But implementing something as serializable is actually pretty easy. I wrote down the steps here. Okay, you have to be able to write to a file. So I included the java.io library to write to a file. All right, so step one, you just say implement serializable. Okay, so you guys can do this in your code if you want to. I'll be posting this code, like I said, later on tonight so you can look at it again. But pretty much you just say implements and then the serializable interface. So I'm saying, yes, I'm going to be serializable. And note that I'm making my node serializable. When I want to serialize an object, and my tree is comprised of node objects, my node object also has to be serializable. So when you're serializing something, all parts of it has to be serializable. Do you think strings are automatically serializable? Yes. Most objects that are created by Java automatically are already serializable. It's because I created this node that I had to tell it to be serializable. Okay. So then I implement serializable here so that I can serialize my root. So note that if I didn't implement serializable on my node class, then my tree would not be serializable. So everything in the structure that you're going to deflate has to be serializable. Okay, so all I did was write implement serializable, voila, my node's serializable. Isn't that easy? There's no methods to write. That's so easy. So then if I want to make my root serializable, I just say implement serializable. Oh, that's so easy. Now note that the root in all the tree is going to serialize. Okay? That's all I had to do. Pretty easy. Now I just have to deflate it and write it and then inflate it. So here's my main. When I want to serialize something, I'm going to write it to this file. I just made up this file extension. Remember, file extensions don't do anything to your computer but tell your computer what app to open it with. So you could put your last name here. Okay, it doesn't really matter. You don't even have to put a file extension, right? All right. Now when you want to inflate the tree, so notice I'm inflating the tree first, then I play my game, and then I flatten the tree or deflate the tree. So you can see that the first time I run this, it does actually fail. And then the second time, it knows to inflate the tree. It doesn't totally fail. It just doesn't inflate a tree if there's nothing there. Okay? So this is just read and write file code. So I just copied and pasted some read and write file code. And when I want to serialize or deflate my object. Oh, this is inflating, sorry. Let's look at deflating first. So when I deflate it, I want to write to my file, right? This is my file writing code. And all I do is say out.write object, and I'm writing my game object. That's all you had to do. You just write your object to a file, and because I implemented serializable, my object is serialized when it writes to the file. Automatically. Pretty easy. They make it this easy on purpose because we do this all the time. Okay? So, the file writing code should be pretty easy. All we had to do is say implement serializable, write the object to a file. That's after I played, I write it to the file. And then the next time I go to main and I start main, main's going to go and look for that file. He's going to find him now that the file is created. Okay, file name. He finds him right here. And then this is how I read him in. Right here. I say game 1. Here's my file. Here's where I'm inputting objects from my file, so you do have to create a new object input stream. The object input stream is connected to the file. These are like Lego pieces. This is your Lego piece that connects to the file. This is your Lego piece that connects your file to an object input stream, so it knows that it's inputting an object as opposed to like an integer or a string. This is telling it, hey, we're inputting objects here. Okay? When I read in that object, it doesn't know what type of object I read in. So this is where you typecast it. And that's a normal thing to do. When you write an object to a file, it doesn't know what type of object it is, so when you read it in, you typecast it. When I typecast it as game 1, voila, game 1 is my old game 1, and I can come here and play, and he's my old root with my old tree and everything. So pretty much, you make them implement serializable, you write them to a file. When you read them in as an object, typecast them, and voila, you have your old tree back. And I'll post this code. You could copy this, paste this code. Your code should work with it too. Okay? And then you'll have a forever tree. You'll have a tree that always plays. And as long as you always put in good questions. I told you guys you didn't have to make a delete method. So you don't have to delete nodes in your tree. But then you'll have a tree that lives forever, right? But he was running last time. I'm not sure if it's my, where I stored him here. I think he is, oh well, we'll come back to him in a second. All right, any questions on serializable though? Pretty easy to inflate and deflate objects. Okay, cool. I'll post this code, like I said, tonight. So after everyone's turned it in, remember tonight's the last night you can turn in that assignment. So, all right. Next thing I have is I'm going to do my interview question today. I'm going to make you all do it. So everybody has to pull out a piece of paper, write your name on the top, and you have to draw a picture of this tree. Picture of this tree. Now, I didn't put all the tree code. We can assume it's a binary tree. So in other words, you're going to insert those nodes in that order. Remember that the key, you just have to write the key. I don't care about the value part. You could write the value part if you want. But this is your key. That's your primary key. That's your node. That's the number that's in the node. Your key. So just draw a picture of the tree. What would the tree look like after it ran all this code? If it's a normal binary tree. Oh no, it's okay. No, don't. Just write the number in the circle, and you can put the data next to it if you want. I won't be that strict. I was going to be that strict, but just draw a picture of the tree. So in other words, insert the nodes in that order, delete those two nodes in that order, and then insert the last one in that order. So you're just drawing the tree like the computer would create the tree. Yeah, not too hard. And do they have interview questions like this? Yes. Okay. If they said, hey, this is a normal binary tree, they probably would make you write the little bracket thingies. But you guys can just draw it as circles, just abstractly. And should I pause this? Maybe I should pause it. All right, let's start talking about hash tables. So you probably have heard the word hash tables. Anyone who's been around computer science or computers have heard of hashing or hash tables. Okay, looking at our Big O algorithm cheat sheet, let's review some of these. This is a good cheat sheet. Yes. Actually, this is one of the more helpful things I have found online. When you go into an interview, they will ask you the big O of some of these, data structures. And normally you could just think through them. Just think, okay, what would be my worst case scenario? What would be my best case scenario? And so I wouldn't just straight up memorize this. I would, just remember how it works so that you can remember it. Okay? So you remember, what was the problem with arrays? Arrays worked in O(n) time to insert something. Oh wait, no, this is a sorted array. So an unsorted array was O(n) time to insert something. How can I tell this is a sorted array? Yeah, because my insertion is O(n) time. Why is my insertion O(n) time? Because I had to move n items to insert that guy in the correct order. So this is for a sorted array. Remember, for an unsorted array, you just stick them in there. It's O(n) time. Do you remember why we wanted a sorted array? So we could use binary search. That was the only reason. So we have these bad insertion times, bad deletion times, but we do have great search times. This should be log n, right? Maybe he's doing linear search. All right, let's look at binary search tree. Actually, we skipped linked list. We know linked list. Insertion in a linked list is O(n) time. Deletion was O(n) time because we just had to rearrange some pointers. It was a couple of steps, but they call it big O(n) time. Now, searching something in into a linked list, remember that you cannot use binary search in a linked list. In a linked list, you have to follow every link to everybody else. So you have to search linearly. That's why your searching is O(n). Okay. And here in this array, this is the only one I would debate. It's bothering me that's O(n), but he's assuming you're not using binary search. But of course, if it was a sorted array, it would be O log n, okay? We need to tell this guy to change that. Binary search is O log n. And that's why over here in your binary search tree, it's O log n for searching times because you're using a binary search. In a balanced tree, you're using binary search. Okay. Insertion, why is it O log n? Yeah, you have to know where to put it. So you do have to go down in your binary tree, put them in the correct location. So that's O log n time to insert him. O log n to delete him because you have to find him. Okay. Now it says worst case scenario ON. Now what is a worst case tree? A tree where all the numbers were inserted in order. What if you inserted numbers in order? You would end up with a linked list. If you inserted all the numbers in order in a binary tree, it's a linked list. Okay. If you insert all the numbers in reverse order, it's a linked list on that side. Okay? So, worst case scenario, that's why it's ON time, worst case scenario. But usually if you have random values, it's O log n. All right, and we didn't discuss any of the other trees, but note that there are other trees out there. The other trees went on beyond the scope of the class. I'm sure you, if you guys are computer scientists, you will find these, you know, someday you will have to interact with one of these, probably. They're not that much harder, you know. They have different rules, but they're set up kind of the same way. Just note that there are different trees. And note that a lot of them all work in the same time. So why do they have all these other trees? For different types of data. Okay, all right. And then we had our sorting algorithms. We won't review that one today. Well, that's our operations. And where do we have our hash? I was thinking that Mr. Hash was in here. All right. Oh, here he is. He was up here. Here's our hash table. Somehow I overlooked him. Look at our hash table. What do you notice about our hash table? It's O1 time. That's the perfect data structure. So search, insert, and delete is all in O1 time. One step. That is an awesome data structure. Now, how come it says nothing for access and nothing over there for access? Well, you guys might not know that yet. But you can't directly access any element inside of a hash table, and that's its detriment. Meaning that you can't go to its index. In fact, we're going to discuss that when we'll look at hash tables, and you'll see why this is a detriment right here. But otherwise, look at that, O1, perfect data structure. Okay, those are some good times. Remember, O1 is the best time. Okay, ON would probably be, the worst time. All right. So let's look at hashing. I think, I put these slides on Blackboard too. Yeah, I did. Okay, the perfect data structure. So we just recalled what was wrong with their other data structures. They were slow in some ways in their insertion and deletions, and, we could have problems with our binary trees. But with a perfect hash table, note that this is a perfect hash table, which is hard to achieve. But with a perfect hash table, you can have O1 times for every operation. Okay? We shall see that sometimes this can be a little slower than O1 because we won't have a perfect hash table. Okay? But it's still pretty close. Plus, it's super easy to program. Yay! Okay. Any downsides? They are based on arrays, so it's difficult to expand after they've been created. So the underlining structure of a hash table is an array. And we all know that once you say the size of an array, you can't make the size larger. You'd have to copy all the entries. Actually, you'd have to rehash all of the entries from the old hash table to the new hash table, which would take some time. So once you say how big it's going to be, it's usually you're going to be stuck with it. If a table becomes too full, performance degrades catastrophically, meaning that it stops working, really. Okay? So, all right. You don't want to make your tables too full. There's no convenient way to visit the items in order, so if I were to ask you, hey, I want to have a data structure where I can visit my items in order, don't ever tell me a hash table. Tell me a binary tree, an array. Okay. You can't visit items in order in a hash table. So if you don't need to visit the items in order, and you know how many data items you're going to have, then use a hash table. All right. So I thought we'd start with an example here. Actually, okay, we'll start with this example. So this isn't exactly a hash table, but this is just a way to store some data. So this kind of is leading into how people figured out a hash table. Okay. So in the beginning, before hash tables, if I wanted to store some employees inside of my program, I would store every employee in my program, and I would just use an array. And I would name my employees. I'd give them numbers 1 to 1,000. Like your employee 1, your employee 2. You give them ID numbers 1 to 1,000. And then whatever ID number they are, I subtract 1 from it, and then I put them into my array. So if they're ID number 1, I say, okay, employee number 1, you're at index 0. Employee number 100, you're at index 99. Pretty easy way to kind of store data. That's how people did it in the beginning. Okay, it worked. But what if your data was not so organized? What if you had to organize the words of a 50,000 word dictionary? What do we use as the index number? Well, you could just name the words 1 through, 50,000. You could. But we're going to think of a better way to do it, okay? So this is what hashing is. You're going to take your data and you're going to convert it to an indexed value. And this is one method to convert a string to an index value. You could follow different methods, different algorithms to convert your string to a value, to an index. But this is just one way. Okay? So what if we just said, okay, we're going to use the ASCII character system, right? Well, something like the ASCII system. And all of our capital A's are going to be the number 1, and all of our B's are going to be a 2, and C will equal the value 3, and Z's equal the value 26. And so then what we'll do is every time we see a C, we'll add 3. Every time we see an A, we'll add 1. If we see a T, we add 20. And if we see an S, we add 19. We add all those up, and we say, okay, we're going to store the word cats at index 43. That's his key. And we just use the letters. We translated them numbers, added them up. Hey, that's your key. It's just a way to translate a word into like some random key. You could have multiplied each one or had them, equal different numbers, but we just did it pretty simple. So it's just a methodology to translate this word into like an index number or a key. Okay? So if we were to do this, and we restrict ourselves to 10-letter words, we're only going to get indexes from 1 to 260. And can you see why? What would a 10-letter word look like? So a 10-letter word, the smallest word we could have, if it's 10 letters, and then he would equal 10 because it's 1 plus 1 plus 1 plus 1 plus 1 is 10. The biggest word we could have would be 10 Z's, and it'd be 26 times 10, it'd be 260. So that's all the indices we have. How are we going to get 50,000 words in there? Okay, so we say, okay, well, let's think of a different way with this. Let's expand on this. Because 50,000 item words in our dictionary stuck into an array of 260 doesn't work. Can you guys see what that is? That's a cat in there. Okay, so we're going to try a different way to do this. We still want to translate our words into indexes inside of an array, but we're going to try this method. We're just going to try it, right? So what we'll say is they have place values. Our numbers have place values. Okay? So like if this was the letter C and letter C equated to 3, we'll say you have the place value 27 to the third power. Because we're just giving them place values because he was the, this would be 19 times, actually I have it here. 19 times 27 to the 0th power. This would be the t. T equated to 20, but we'll multiply it times 27 to the first power. So we're giving them place values. We're giving them, if they're the first, if they're the letter on the right, like the S, then we get 27 to the 0th power, right? Does that make sense to you guys? Okay. Just like place values. Because there's 27, or 20, there's 26 letters, huh? But we just use 27. I forget why you chose 27. I think because, I don't know, I had some methodology in using 27, but we just used 27. Okay? All right. Oh yeah, because you always do one more than the number of possible values. All right, so we just gave them some place values. So then we figure out this number, and what's that number going to be? Right, a really big number. It's going to be a huge number. Okay, and you can kind of think, okay, that was just the word cats, C-A-T-S, and that was a huge number. What if I translated my 10 Z's? If I translated my 10 Z's to this really huge number, I'm going to get 7,000 billion or 7 trillion, which is way too big to stick inside of a computer, inside of an index and an array. If I tried to make an array of 7 trillion, my computer would not do it. It's physically impossible, okay, to do that. So we can't do it that way. Okay, well, let's build on this. How could we make this work? And this is how we're going to make it work. We're going to follow this methodology still. So we're going to take that character, give it a number, 1 to 26, multiply it times its place value. We're going to get that really huge number. And then we're going to use the modulus operator to make it into a manageable number. Okay, so what does the modulus operator do? It returns the remainder as a whole number. So if I modulus something by 1,000, I'm going to get the number 0 to 999. You're never going to get over what you modulus it by, because obviously if you get over it, it could have gone into it again. It's not going to be part of the remainder. Okay? So all numbers modulated or modulused with 1,000 will return a number between 0 and actually 999. So 0 and 1,000 exclusive of 1,000, right? Actually, it could be 0 if the remainder was 0. But it could never be 1,000. All right. So to change text to a number, we convert the word into a huge number by multiplying each character by a power of 27. So we take that character's value, like C equals 3, A equals 1. We multiply it by its place value. We get a gigantic number. And then we use the modulus operator to squeeze the huge range into an index range we can store in the computer. And that is a real-life cat. So we take this huge number, we modulus it, and we make it into a manageable number. All right? So here's our methodology. This is our hash. This is a version of hashing something. This is what hashing is. We change our text into a number. We use an index range that's... Okay, so we're going to need an array to stick this in. How big of an array should I use? Should I use an array that's only 50,000? I have 50,000 words I want to store. Should I use an array that's only 50,000? Because every word's going to hash to a unique index, right? If I follow this methodology to hash my text, do you think every word in the dictionary is going to hash to a unique number? Probably not. Common sense tells us probably not. Okay? Some words will indeed hash to the same index. So, kind of the rule with hashing is that you want to use an array or an index range that's at least twice as big as the number of items you want to store. Because some values are going to hash to the same indices, but if I use an array twice as big as the array that I need, then I'll have more room. When I modulus it by 100,000, we'll get broader indices, okay, and then they won't collide to the same index. Okay, that's kind of a rule with hash tables. You want to use an array as twice as big as the numbers you want to store, which in essence makes it inefficient, right? All right, so you are using an array twice as big as what you would normally store if you just used a regular array. So you're using twice as much memory to make a hash table. So 50,000 words in a dictionary would use an array with a size of 100,000. So you would take each word in the dictionary, you'd modulus it by 100,000, it would become an index in our array, and that's where you would store the word. Okay, and the definition. The cat fits in the bottle. So I just made up a hash function. That was a hash function. I took a value, I hashed it into an index, and I used it inside of an array. I put it in an array at that index. That's what hashing is. The perfect hash function would hash every word in my dictionary to a unique address, to a unique index. That would be the perfect hash function. Okay. Is there a perfect hash function for a dictionary? Is there a way to make to hash every word in the dictionary into a unique index? There might be, but we haven't found it yet. Maybe that's what you guys will do. That means, is there a way to kind of manipulate the letters in a way where every single word in the dictionary is going to hash to a unique index? It actually hasn't been found yet. You can get pretty close. Okay. So, all right, you are going to have collisions, meaning that two words are going to hash to the same index. An example of this are the words demystify and melioration. So how did we hash these things? D was the number 4, right? A was 1, B was 2, C was 3, D was number 4. And this was to the 0th power, 1, 2, 3, 4, 5, 6, 7, 8. So D would be 4 times 27 to the 8th power plus, so you guys know how to do this, right? I'm not going to do the whole thing. You guys can if you want. But they do hash to a really big number, and when I modulus it by 100,000, they both have the same remainder, and so they both index in the array at the same location. Okay. So how do we handle collisions? So we're definitely probably going to have collisions because a perfect hash table is hard to come by. Okay, it's hard to figure out a hash where your data is going to all be uniquely hashed. Okay? All right, so there's two ways to handle collisions. You could either put the second one into an empty cell near where it should go, and we'll discuss this. This is called open addressing. So you just say, oh, well, you belong here, but I'll just put you over here. Okay, and there's some methodology to it. Okay. Or you put the second item in a linked list, or a binary tree, or an array at that location. So you would have an array of arrays, and when they hash to the same index, you're putting it in that array that's at index 465. Or you make an array of linked lists, and when they hash to the same index, you're adding onto that linked list. So it becomes like, you know, two-dimensional. Remember to visualize it. So, okay, cool. We'll draw a little picture. So we have our array. Okay. And let's say demystify goes here. Then we come to put melioration in here. Open addressing would say, okay, well, we'll put melioration right here. Okay. And there's some methodology to that. So that's open addressing. And then separate chaining would be, okay, well, I'm going to make a linked list here, and we'll put you here. And then if another word comes in that also hashes to the same index, I would add him onto the linked list. So then you have an array of linked lists. Okay? That's one way that you could handle it. So let's look at open addressing. So open addressing, there is some methodology to open addressing. You just don't say, hey, go over there, or else we can't find you again, right? You have to have some kind of algorithm. All right? So a data item can't be placed in the array index where it should go because, you know, there's another item already in there. So there's three ways that we're going to talk about for open addressing. So open addressing, you can either do linear probing, quadratic probing, or double hashing. Okay, so linear probing kind of does what we just talked about. If they hash to 0 and there's somebody in there, then you just go to the next open location. Okay, so here's the example here. Key 3 also hashes to index 4. So they just look for the next open spot and they put it in there. Okay? All right. Do I really want to open my applet? Let's see if my, up until a little while ago, my website has not been working. So my unlimited server space is actually limited. Did you guys know that? When you go and buy unlimited server space. So he's working at the moment, but I still have to go in here and fix him. He's been, I don't know. Okay. Let's see here. 39. Here's our hash. He might fail. Yay, he did not fail. Okay. We'll use our magnifier. All right, cool. So here's our hash table. So note that, there's a lot of empty locations. And there's a lot of empty locations because remember that you want an array twice as big as the number of elements that you're going to store in there. Okay, this is because you're going to have to do some kind of linear probing. Okay, or you have to do separate chaining, or you have to, well, separate chaining is different, but you have to do some kind of, open addressing. Such as, let's insert a number that's already in here. So if I insert number 900, let's do one easy, 986. If I try to insert the same number, then he's going to hash to the same index. Well, 986 might not. Let's do 761. I know that he will hash to the same address because there's no one else around him. I know that he hashed to this address, and that's where he goes. Okay. So if I try to insert another 761, he should hash to number 41. So they're doing their little hash algorithm, whatever they're doing. I don't care what they're doing. But they're taking this number and converting it to index 41. Okay. It says the cell 41's occupied, and they're going to use linear probing. Linear probing just says, okay, go to the next open spot and put them in there. That's pretty easy. So you just say index plus plus, see if it's open. If it's open, you put them in there. Let's try 23. 23 should index to 24, or he could index to 23. You see why he could index to 23? He might have already been linear probed. He might have already had a collision. Okay, I'll insert him. See, he did hash actually to index 23. So the 23 that's in there was already linear, probed in there. So it's going to go to the next one. Oh, it's taken. Oh, it's taken. Oh, it's taken. Oh, it's taken. Oh, okay, we'll put them in here. So can you kind of see the fault with linear probing? Okay. If I want to go and find my element again, I go and hash at that index. And there's somebody else there. I still don't know if my item is in the hash table or not. I have to search until there's an open spot, and then I know he's not in there. Okay, so you can kind of see the detriment here. Here's another fault with linear probing. What if I deleted something? What if I delete the number 325? So I'll go to 325 and I'll hit delete. Oh, it actually hashes to index 25, so he's where he should be. And I delete him. And then I want to go and delete number 23. It's going to hash to index 23. And note that it had to go and find the other 23. Okay, what if I want to delete number 23 again? Now, if there's nothing in those locations, how does it know that 23 could be over there? So note that there is not nothing in those locations. What did we put in there? Yeah, you have to put a marker. So when you delete something in a hash table that's using linear probing, when you delete stuff, you have to put a little marker in there that says, hey, there was something here, so what you're looking for might be down the line. Okay, so keep looking for it, which it does. See how it kept looking? So when you delete something in linear probing, you have to put that marker in there. So then it knows next time you go in there to search or delete that there was something there and that what you're looking for might be beyond his index. Otherwise, linear probing is pretty easy, right? You can start to see the faults when your table gets really full. Okay? Then you're going to have a lot more collisions and objects are not going to be where they need to be. So if I let's insert 23 a couple times. Notice that when you insert 23 and there's a marker, it will put it in the empty hole. Okay. Now notice my table is starting to get really full. Where's the next 23 going to be? Yeah. So 23 hashes to index 23, and we're putting him at number 37. That's really far away. Note I had to look through, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different places before I found him. Or where I found an open spot to put him. So you can see that if you have clumps in your hash table, if somehow you do your hash and the way that you do your hash, it starts making clumps in the indexes, you're going to have a problem. A perfect hash would make everything distributed evenly and not have any clumps. Well, the perfect hash would have everything unique. But a good perfect hash, well, maybe not perfect, but good hash would distribute things evenly and not have clumps. Okay? All right. So that's linear probing and a hash table. Okay, so that's linear probing. Of course, there's other ways to probe. So some problems with linear hashing, clustering is called those clumps. Okay. When things start getting really full, it's called your load factor. And if your load factor is 2/3 full, it's going to start not working. Okay. You're going to have to, it turns into like a linear search, ON time. You know, not very good. All right. But you could just make the array bigger, right? Yeah, you can make the array bigger. But then you would have to rehash all of your key values because the hash algorithm worked with the size of the array. And this can take a very long time for a very large data structure. So note that if you do have to make your array bigger and rehash, you will want to do it over a weekend. Okay? It takes a really long time for hash tables in real life that are really large, like, you know, over 1 million items. It takes days, okay, in a computer. And we saw that when we were doing our sorting test. That took a long time. This takes a really, especially if you have a complicated hash. Okay? Complicated hash algorithm is going to take a really long time. All right, so that was linear probing for open addressing. That was open addressing, linear probing. Here's open addressing quadratic probing. They're trying to improve on the probing technique. So another solution to collisions and clustering, instead of placing the element in the next available slot, how about you look for an open slot a little bit farther away? Such as, okay, we'll look at the next spot first. We'll say, okay, we'll look next door first. And if next door is taken, then we'll look 4 houses down or 4 spots down. If 4 spots down is taken, then we'll look 9 spots down. If 9 spots down taken, we go to look 16 spots down. If 16 spots is taken, where do we look? Yeah, we'll go and look at 25. Okay, good. It was x plus 5 squared. Okay, so quadratic probing, this means, hey, we just look further and further away each time instead of going next door. Does it work a little bit better? Sometimes it works a little bit better. Because now you're going to get away from the clump. Right? If there's clumps in your hash table, you're moving him farther away. Okay. Just note that when you go and search for these values, you have to search in the same way. Right? So some tips for a good hash. These are well-known tips out there in the real world. Make the size of the array a prime number. Why would you make the size of your array a prime number? Think about what you're doing with the size of your array. You're hashing a really big number and then you're dividing it by the size of your array. So if you make the size of your array a prime number, you guys know about prime numbers? You guys know about prime numbers. What happens when you divide something by a prime number? Huh? No, we don't get one. It becomes more random. You're going to get more random numbers because nothing's going to be divisible by that number. It's just a known fact that when you divide something by a prime number, you're going to get more random numbers. Okay? It allows the keys to be more randomly placed in the array when divided by the size of the array because he's a prime number. So the rule is, make the array at least twice the size of the number of items you're going to insert, and then find the next prime number. So if I wanted to store 50,000 words in a dictionary, which, okay, I would make the size of the array 100,000. And what's the next prime number after 100,000? You could ask Google, huh? I don't know. So next prime, or look for a prime number list. Let's see how smart Google is. They think they're so smart. So we would use 100,000. Look at all these prime numbers. There are algorithms to find prime numbers. You can look at an algorithm online to find a prime number. Oh, there we are. So the next biggest, highest prime number, bigger than 100,000 is, I think it's 100,008, right? Dun, 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 right here. Uh-oh, I think I went to 1 million. Let's say we were storing 500,000 words. 500,000 words, so we want an array of at least 1 million. So we would go to the next prime number bigger than 1 million, which happens to be 1,000,003. Okay, I went too far. So if we wanted to really do the 50,000 with 100,000, it's actually way back here. There's probably an easier way to find these using some math. Oh, it'd just be 100,003. Duh. Okay, cool. Okay, cool. So that's how big I would make my array, and that's what I would use in my hash function. So then I would get less collisions because they would hash to more unique addresses. That makes sense, right? All right. So there's some problems with quadratic probing, of course. Okay. This happens because we always are moving the same calculated distance away. So if we get clumped here, we're going to start getting clumps here, and that does happen. Okay. So we need a way to move away randomly, but we also have to find what we're looking for again. So it can't be too random. We can't just say, oh, get a random number and move that away, because how are we going to find them again, right? So you can't be too random, but it needs to be more random. Okay? So this is called secondary hashing, or double hashing. So what you do is you hash once, you find their index. If someone's there and it has a collision, then you hash them again, find the next place where he should be. Okay, it's called double hashing. So you use the key in the equation to find the length of the step. So an example would be constant minus key modulus it by some constant. That would be a second way to hash them. Say, hey, if there's somebody there, we'll do this step size here. That's how far away you're going to be. It's a little bit more random. All right. And then separate chaining is like what I wrote on the board. Here's another picture of it. So this is as opposed to open addressing. So in open addressing, your collisions are resolved by looking for another open cell, where separate chaining, we say, oh, you hashed to index 4, you are going to be at index 4. This adds you onto the linked list. You can make it a stack. You can make it a linked list. You can make it another array. You can make it a binary tree. So you could have a hash table of binary trees and put them inside binary trees in your hash table. A lot of times hash tables are created out of other data structures. Okay. All right. All right. So this has to do with my old book, so don't read that. All right. Actually, for your guys' exercise, and this is actually going to probably be our last assignment before our final project. And I think your final project will just be a presentation, okay? All right. Yeah, and we have our final test. We'll study for that. I do have actually a really awesome final exam, right? All right. But this is your last, homework assignment. It has to do with hashing. Hashing is not hard to implement. We'll look at the code here in a second. Some example code of some hash. But this is the homework assignment I gave you guys. And for this assignment, you're going to implement a simple hash map. And you can even use the code I gave you. We'll look at the code. We can create this hash map to hold entries for a dictionary. Our dictionary object is going to contain the word and that word's definition. So, for example, I think I gave you guys the text file. I gave you guys an example dictionary you can use. So the first word you read in will be the word, and then the rest of the string in that line will be its definition. So it's actually really easy to read in. I thought we could start this together. Read them in. Make sure we can read them all in, right? That'll be your class assignment today. So know how many words are in here? I don't even know. I'll have to count them. If I wanted to figure out how many words are in here, how could I figure it out? I could count the number of lines, or I could paste it into Excel. Oh, there's a blank one. Oh, I'll have to make sure I remove that blank one. So before you actually take the data, make sure I delete this blank one. The blank ones will cause you problems. Dang it. There are 48,040 words in here. So, just because we were practicing this, how big should I make my hash table? How big should I make my array? Twice as big as that and a prime number. Aw, hopefully it was recording me. This is why we have problems with the record. This guy was off. I don't think the whole time. Maybe it's when I dropped him. Oops, I shouldn't say that out loud. Okay, so you hover over buffered reader. Okay, you import it. You hover over file reader. You import it. You change this file name to your file name. And the code I copied didn't have a catch part, and that's what it's yelling at me for. So actually, here it is. I need to copy this little part. Man, this buffered reader throws all kinds of exceptions. So I could just throw him out, but we'll catch him. Oh, another exception? I thought we did the file not found exception. All right, we just had to restructure them a little bit. But there we go. Now we got them all working. No, it's just because buffered reader has more exceptions than other, because more things could go wrong with him. Why do we have these exceptions? Do you guys know why we have these exceptions? When you first learn about exceptions, you're like, oh, why do they have these? They're causing me problems. But in the long run, it's actually a good thing, because when things go wrong, it's telling you that things are going wrong. So if something went wrong with our file, we can do something here to recover. So actually having these exceptions makes Java a better programming language in a lot of ways. And yes, sometimes they're a headache that you have to catch them, but it makes it so you can recover from failure, from it failing. Remember that if this fails and it can't find that file, it throws this exception. I can do something here to maybe try another file, try another place, ask the user for the file name. Okay? So note how I fixed that. So one way that I fixed it is I declared this in the try block, because this is what was throwing the error. So he had this instantiation had to be in the try block, so that I could catch that file not found exception if it were to be thrown. And then the input-output exception was thrown by, what was it, read line? Yeah, you can see it throws the IO exception. So if something goes wrong with my input-output, he's going to throw an exception and come down here. No, if you don't catch these exceptions, Java forces you to catch the exceptions. If you don't catch them, then you have to throw them back to main, and then you have to catch them there. It makes you take care of them. So it's best just to take care of them here. And you could do a little system out print line to yourself. Like file not found. So if that exception were to be thrown, I can say, hey, my file wasn't found. And then if this exception were to happen, I could say IO error. So input output error. Because that's my input output exception. All right, so if you got this in there, read in your file and just notice that, what is this guy doing? We got to do something smart with him. It's making a new string, so it made something called a string builder. So in other words, it's just a string. In other words, it's concatenating all the lines onto the string. It's using a line separator. And then it's reading in the next line. It's reading on all the lines and building a string builder with them. What do I want to do with that string builder? Let's just print them out. And Mr. String Builder was declared in here. So I'm just going to take that declaration and declare him outside of my loop so that I can use him outside my loop. So then later on I can use him. And he just wants him to be initialized, so just initialize him. And he is an object, so we have to initialize him as an object. You could use that previous code we used before. It doesn't throw quite so many exceptions. Note that this one throws lots of exceptions because we are using a higher level class called a buffered reader. It is doing some buffering. You guys all know what buffering is, right? It's making a little storage space in our memory where it's holding things so that it can feed things into our program quicker. Remember to add comments as you figure things out, right? All right, now read in some stuff from your file. And then this should print it out right here. Actually, I don't even need to declare him here anymore, right? Cool. Alrighty. So call that method, read in file. And then we want to put our file name, dictionary.txt. I guess I should check that this actually works. Oh, it worked. Great. Awesome. Okay. We kind of assumed that he worked. So our goal today is to get some file reading code to work. Now remember, you don't have to use this file reading code. You could use some other stuff you found online. I really don't mind. What we're reading in is not heavy information. 46,000 lines is not that much. 6,000 lines of characters is not that much. I think this is a good place to kind of call it quits today.